This is digital circuits. And we're doing the study guide for chapter 17 to 7 to 12. All right, problem number 1. We got binary stuff, and we have 2's complement stuff, and we have gray, and we have decimal. Okay, so the first thing we have is we have a binary number, 0, 1, 1, 0, 1, 1, 0, 1. If I can write it down right. And I guess we'll go to 2's complement first. All right, so we go in and change all the 1's to 0's and all the 0's to 1. And then we're going to add a 1. And then we're going to write down the answer for 2's complement. 1, 0, 0, 1, 0, 0, 1, 1. Okay, and then we're going to go to gray next. Okay, so we can start with the number again. 0, 1, 1, 0, 1, 1, 0, 1. And now we're going to go to gray. And we're going to go and take the first number and keep it, 0. Do a exclusive OR on the next 2, get a 1. Exclusive OR, get a 0. Exclusive OR, get a 1. Exclusive OR, get a 1. Exclusive OR, get a 0. Exclusive OR, get a 1. Exclusive OR, get a 1. And write down the gray code, 0, 1, 0, 1, 1, 0, 1, 1. And then we want decimal. All right, well, unit, 2, 4, 8, 16, 32, 64. So we got a 64, a 32, and a 13.
Exclusive or
exclusive ORs. Yeah.
Exclusive or, okay.
4, 8, 9, 109. So we'd say the decimal is 109. But we probably would have put that in our calculator, and had our calculator told us it was 109, we probably wouldn't have done what I did. All right, so now we're going to do it again, and we start with 2's complement. 1, 0, 1, 0, 1, 1, 0, 1. Now, do we change that to gray? No, we can only send binary to gray. So we got to change it to binary first. 0, 1, 0, 1, 0, 0, 0, 1. Well, actually, that's 1, 0. And then we're going to add 1, and we're going to say the binary is 0, 1, 0, 1, 0, 0, 1, 1. And then we're going to go for the gray. We're going to keep the most significant digit, do an exclusive OR, 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 do an exclusive OR. 1, 2, 3, 4, 5, 6, 7, 8 looks right. So gray, 0, 1, 1, 1, 1, 0, 1, 0. And then we need decimal, and unit, 2, 4, 8, 16, 32. So we have a 64, we have a 16, and we have a 3. So that means we have an 83. So we put an 83 over there. And we're doing this all for one lousy point. All right, now we have binary, 2's complement, gray, and decimal.
When you have a 1, how do you know if it's 0, 0,
Okay,
or 1,
so we have a 0, 1, 1, 1, 1, 0, 0, 1. Okay, so we keep the first guy, he's a 0. We then take that answer and exclusive OR with the next guy, get a 1. Take that answer, exclusive OR with the next guy, get a 0. Take that answer, exclusive OR with the next guy, get a 1. Take that answer, exclusive OR with the next guy, get a 0. Exclusive OR with the next guy, get a 0 exclusive OR. With the next guy, I get a 0 exclusive OR. With the next guy, I get a 1, 1, 2, 3, 4, 5, 6, 7, 8. So my binary is 0, 1, 0, 1, 0, 0, 0, 1. Okay, so now I got my binary. So when I had the binary and I was going to gray, I was exclusive ORing the numbers up that they're there. But when I go from gray to binary, I take the output. I take the output and do an exclusive OR with the output to the next guy.
Okay, then it matches whatever the previous digit was, if it is 0. Okay.
And then I'm going to find 2's complement, so 1, 0, 1, 0, 1, 1, 1, 0. So the 2's complement answer is going to be 1, 0, 1, 0, 1, 1, 1, 1. All right, because I added 1 to this guy. And now I'm looking for the decimal unit, 16, 32, 64. So I got a 64, a 16, and a 1. So that looks like an 81. 81. All right, next one. I got a 45 decimal. And I want gray. Well, I can't get to gray from 45. And I can't get to 2's complement from 45. So I have 45. So I'm going to put down a 32 guy. And I'm going to subtract, and I'm going to get 13. So I don't need a 16, but I need an 8. I need a 4, and I need a 1. 1, 2, 3, 4, 5, 6, 7, 8. We're going to put it in 8 decimals, 8 places, because that's what we're going to do, because all the other ones are 8, right? All right, now we're going to go for 2's complement, 1, 1, 0, 1, 0, 0, 1, 0, add 1, and our 2's complement number 1, 1, 0, 1, 0, 0, 1, 0. Now we could have put minus 45 in our calculator and asked it to turn it to binary for us, and it would do that for you. It just give you more 1s at the beginning. All right, now we got to look for gray. So I've got 0, 0, 1, 0, 1, 1, 0, 1. What's your problem? Oh yeah, this right here's a 1. Is that all? You wanted me to add the 1 too? I have to do everything? Okay, well, I guess I'll add the 1. I think I am, anyway. Dr. Carson, I have to add? Really? Okay, where were we? We're trying to turn this thing into a gray number, and everyone is slowing me down. All right, so I got a 0. I got another 0. I've got a 1. I've got a 1. I've got a 1. I got a 0. I got a 1. And I got a 1. So my gray code is going to be 0, 0, 1, 1, 1, 0, 1, 1, 1, 2, 3, 4, 5, 6, 7, 8. At least I have the right number of digits. Whether or not that's absolutely correct, either we did it right or we didn't. All right, questions about problem number 1? Should not take the rest of your natural life, but you can use your calculator, so you don't have to do it manually. Not for gray,
For the grays.
but you can for 2's complement. Yeah. Well, if you're in binary, yeah, just put it. Yeah. 45. Put a minus sign in front of it. Convert to binary. It'll tell you the 2's complement number, and then write it down to 8. The least significant 8 bits, because it's going to give you 10 bits because your calculator is doing 10-bit math. All right, so back to what we're doing. I want to know on number 2 whether or not this circuit's going to work. So I got 2 numbers, and that goes in, and this goes in, and then I have a thing like that. And he comes in and he comes in, and then I got coming up here, and I got something that looks like that, and that goes over there. All right, so I've got that guy there, and he comes over to there, and I want to know whether or not the summation is correct. Which one's the summation? Well, I don't know. I can't really tell. It's not telling me. And whether or not the carry is right. Well, the carry is supposed to be AB, actually A naught, B naught. And the summation is supposed to be A naught exclusive OR B naught. So that's what I'm looking for. So now the issue is that what I have? So I got A or B. I've got A, B, naught. Over here, I've got A, B, naughted, and A or B. And then, well, we'll look at him first. So I got A naught or B naught and A or B. Okay, so that's A naught, B naught, that's a 0. I got A naught, B, or A, B, naught, which is correct for the summation. So the summation guy is okay. So now we're going to look at the carry guy. So I've got A, B, naught, A or B, and A or B, the entire thing knotted. Okay, well, that's what it is. So we've already done the bottom guy. So we might as well just say naught A naught B or A B naught A or B. Okay, so then we'll keep the naught guy, and that's 0. It goes away. I have A B naught or A B naught, and the other guy goes away, and then it's knotted. Okay, so I got.
At the beginning of your purple there, don't the A or B and the A or B becomes a single A or B? So it's
No.
A, B, not?
No, not
Yeah.
necessarily.
A or B?
No, not necessarily. Yeah, it would be. Yeah. All right, so I've got A exclusive or B knotted is what I've got. Well, that's not that. So the carry is wrong. Carry wrong. And that's all we care about. We just want to know if something's wrong. So if this were the summation, it would be okay. If it wasn't the summation, then it's not okay. It's not marked. Now in the test, I'm going to mark one as the summation and one as the carry, and of course have a different circuit there, naturally. Number 3. It says I want to take 4-bit binary. Okay, so I got A0, B0, A1, B1, A2, B2. How come I got them in alphabetical order backwards? 3, B3. It doesn't really matter. And it says I want to take exclusive ORs. All right, so I'm going to take an exclusive OR. Exclusive OR. Exclusive OR. Exclusive OR. And then it says I want to take a NOR gate. Okay, so I'm going to have a NOR gate. Boom, 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 And I'm going to say that this is my compare circuit. And then I'm going to say, well, does it work? Well, if both of them are the same, I get a 0. If both of them are the same, I get a 0. If both of them are the same, I get a 0. If both of them are the same, I get a 0. So if they're all of them are the same, I get a 0 going into the OR, which gives me a 1. If any of these are different, they're not the same, I get a 1 going in the NOR, and then I get a 0. So the circuit works. We can move on. The connections shown to an 8-line multiplexer determine why. So we could determine why, or we could determine why not. That was my phone going off. Stupid thing. Anyway, it thinks it's voice activated. All right, number 4. So first thing we're going to look at is ABC, which is my selector switches. And I see a 0, 1, 1. 0, 1, 1. So that means I'm selecting a 3. So I look at D3, and D3 is high. Okay, so if D3 is high, and that's what I've selected, then Y is going to equal 1, and I'm done with number 4. What? I look at the it's a multiplexer. Somewhere on the multiplexer has to be lines that are selecting which one I select. Where are they? They're at A, B, and C. Can they be any place other than A, B, and C? No, they can't be. Who's the most significant guy, A, B, or C? C is the most significant guy. And I see I have 5 volts hooked up to A and B, and I see C is grounded. So that means I have 0, 1, 1, which is a 3, which means I'm selecting D3. I look at D3, and it has 5 volts hooked up to it. So that D3 has to go to Y. Okay. So 1, I know it's a multiplexer. 2, I know there has to be something selecting what I'm selecting. Once I know what it's selected, it has to go to the output. Is the output Y or is the output W? Yes, it's both. Okay. And is the gate on? The gate is grounded. It's a negative gate. Therefore, the chip is on. I'm going to see a 1. So if I put a 1 on the gate, then the gate's off, and I'm not going to see a 1. I'm not going to see anything. It's going to be an impedance high. It's not going to be a 1 or a 0, because the gate's not on. All right, enough? Yeah. So just pick 1 or 0, and you get 50% of it will be right. It can't be anything other. So if you pick, so if you go and you pick a 2 for what Y is, and that's going to be wrong because this is a digital circuit class. So you have to pick either 1 or 0. Okay, good enough?
So it's always C first, then B, then A. So 0, 1, 1. If that ended up being a 0, 1, 0, Y would be 0.
If it were 0, 1, 0, that means it's selecting the D2 guy, and the D2 guy is grounded, and Y would be 0. Correct.
I understood.
Yeah, and it's a very easy problem to change some wire on so it would be different in that problem, right?
I understood it. I can't believe it.
Yeah, something's wrong here. All right, number 5.
So I'm going to get at least a 10% on this test.
Yeah, probably. Now, this says wired AND. In a wired AND circuit, it's ANDed, the chips are ANDed together even though there's no AND there. That being the case, X is going to be A0, and B naught and B C naughted. Does it say I have to simplify? Yes, it does. What a bummer. Okay, so that means I got A naught, B naught, B naught or C naught. I got A naught, B naught or A naught, B naught, C naught. I got A naught, B naught, 1 or C naught. I've got A naught, B naught, and I'm done. So now I've written the Boolean equation and I have simplified it. Oh, I'm not done yet. I still have to do Y. Alright, so bummer. So again, it's a wired AND. So I have A exclusive NOR B and B or C naughted. So that's what my Y is. Now I'm supposed to simplify it. Okay, so I've got A naught, B naught, or AB, and B naught, C naught. Okay, so I've got A naught, B naught, C naught, or nothing. So I don't have to write the or nothing, I just recognize it as or nothing. So my final answer is just Y is equal to A naught, B naught, C naught, if I can remember to remove my hand from my thingy.
Go back to the experiment.
But the key is it's a wired AND. The AND gate isn't there. It is there because I built the chip so it doesn't have to be there and be AND anyway. Oh yeah, that's one way to look at it. Number 6. Why is it important to store MOS ICs in anti-static foam? So this is a 3-letter answer. E S T. You can spell out EST if you want to. Electrostatic discharge. So electrostatic discharge, something that you can't even feel because it's not high enough for your own body to feel it, is enough to destroy a CMOS chip. Okay, number 7. Take my word for it? Yeah, we have that to destroy one in the lab, despite all your best efforts.
Put some carpet in there.
Yeah, I can imagine. Yeah, that would definitely do it. Yeah, no carpet in my lab. Okay, so I've got a gate. Okay, this is an SR flip-flop. Okay. All right, so I got a gate. So unless the gate is high, nothing's going to happen. All right, so I got a gate. I got some S guy, and he's going to start high, and then he goes up and down there, and he goes up and down here, and then I've got some R guy, and the R guy goes up and down there, and he comes over here and goes up and down there, and he comes over here and he goes up and stays up. Okay, so now we gotta draw a graph of Q. Okay, well, the gate's on and I'm setting, so Q is going to be high. The reset occurs The gate is still high, I'm going to go low.
So even though there's a gap between the set and the reset, and the set is low because the gate's high, it stays high?
Once it's set, it can only go unset if it's reset.
What if the gate goes off and it's not reset, it's still high?
Yes, it would stay high, yeah. So it stays high whether the gate's there or not. Okay, now the set happens, but the gate is low, so it doesn't care until the gate goes high. As soon as the gate goes high, then Q will go high. The reset happens, but the gate is off, so nothing's going to happen just because the reset's on until the gate comes on. And then the set happens, so I set again. The reset happens, so I reset again. Okay, so I'll start at the beginning. At the beginning, God created the heavens and the earth. And on the seventh day, he rested and the set was set. Okay, so the gate's on, the set's on, so I'm going to start high on Q. The reset occurs while the gate is still on, so the reset sends it low. I stay low until the gate is on and the set is both on at the same time, at which time I set again. My gate goes high, my Q goes high. That the reset occurs with the gate off is irrelevant. Q stays high. But the reset's on and the gate happens. I go low. I'm low, the gate happens and set happens, I set. I go high again. The reset occurs, I reset. That's my Q. Okay, good enough? One more time?
Please.
Okay, the gate has to be on for the set or reset to have any effect. If it's not on, the set and reset won't have any effect. Set means I go high. Reset means I go low. At the beginning of the problem, the gate's on, the set's on, I am high. So I'm starting high. The set goes away, doesn't matter, but the reset occurs while the gate is on, so I go low. The set comes on when the gate's low, it doesn't matter, nothing happens, but the set's on when the gate goes high, so I set, and my Q is high. My Q stays high until I reset when the gate's high. I go low, I then set again because it's set in there, the gate's still high. I have a reset with the gate low, with the gate high, so I go low. Nothing else happens for the rest of the problem. And I had to draw all four of them. You guys only get to draw one because the other guys will be there. But it's a gated SR flip-flop. It will not change unless the gate's high. Now, I could give you a gate not, right? I could give you a negative gated guy, and in which case it'd go the other way. But that would be cruel and unusual punishment, so I'm probably not going to do that.
It won't change unless the gate's high and the set or the reset's doing something?
That's right. It's not a positive edge trigger. It's not a negative edge trigger. It's not a clock pulse. It's a gate. The gate has to be on for either the set or the reset to work. Okay, number 8. Everybody says I should skip 8? No, okay, number 8. What additional synchronous operating mode does the JK flip-flop have that the SR flip-flop does not have? And that's the awesome toggle. That's the toggle. Probably not going to be different on the test because I'm going to word the stupid problem differently. You know, it's not like there's any other thing I could ask in its place. Is there? No. If you email me if you have a better question for the test. I can imagine. Number 9. But there, there is a certain requirement that you guys all get A's, right? So the test has to be somewhat sort of easy. A particular Schmidt trigger inverter has a positive going threshold and a negative going threshold, and a typical high and a typical low. Sketch the transfer function of V in versus V out. All right, so here's my V in. Here's my V out, which makes it typical. Okay, and I got a 2 volt guy there, 2 volts. And I got another guy here that is 0.7 volts, and I've got a 3.8 volt guy there, and a 0.3 volt guy there. And it is an inverter. Okay, so that means when I'm high, it will be low, and when it's low, I will be high. All right, so I'm going to be coming in like this, blah, 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 blah. I hit there, I go up, blah, 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 and I go that way. When I go back the other way, I come this way, and then boom, I go down like that. There is my transfer function. And because it's an inverter, when I'm low, I have to be high, and when I'm high, I'm going to have to be low.
Okay, so the first line you drew represented, was it 0.3 volts?
It represents, it's at 0.3 volts, it's at 10 volts going in, and it's giving me 0.3 out, and when I get to 0.7, I go back. And when I go the other way, I have to get all the way up to 2 before I can drop down. Okay, so if I was going to make it different on the test, I might not have the word inverter there, in which case it wouldn't do that. It would do something slightly different, but I think it won't be that much of an issue. That's what I think anyway. Number 10. And this is where you may have to take off your shoes so you have enough things to count with. Let's see. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So the first guy is mod 10, because there's 10 of them. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Shit, I ran out of time. 12, 13, 14, 15, 16, 17, 18. Okay, so I think that's mod 17. 3, 5, 5, 4, 3, mod 3. 7, 6, 5, 4, 3, 2, mod 6. 1, 2, 3, 4, 5, mod 5. That's all there is. There ain't no more. And if you skipped saying mod and you just put 4, 10, 17, 3, 6, 5, I couldn't argue with that answer. That'd be perfectly okay. So you don't have to misspell mod if you don't want to. Okay. So the modulus is how many are there? All right. And again, that's a very simple question to change so that the answers are different on the test. And but the question's going to be there. Number 11. All right, so we have the twos terminal, the 2, 1, the 2, 2, the 2, 3. Notice that I skip one. I will skip one on the test also. So at the 2-0 terminal, I'm going to have half the frequency I started with. So that would be 2.7.
2.7.
2.7 megahertz. Expect a minus 0.1 for units in the case you don't bother to put them down. And then I'm going to divide by 2 again, 1.35 megahertz. And then I got to divide by 2 again. And I would be doing this in my calculator, except I'm doing it in my head.
It'd be 67. 66.
60, let's see, 60, no, 67.5, 67.5 kilohertz. And then half of that, 37.5 kilohertz. And then because I skipped one, I got to divide it twice. So on the side, I'd go in 1, 6, 8.75 kilohertz. And then I divide it again and say I'm dividing by 2. So that's 84.375 kilohertz. And again, I wouldn't do it in my head. I would be doing it in my calculator and writing it down, but I didn't bother to bring mine today. Oh yeah, I got one in my pocket, so I can check it. Do I need to check it, or is it right? Okay. All right, that's all there is. There ain't no more. I would expect the same problem with a different number of starting frequency. Okay, number 12. Number 12. Okay, so I've got a decade counter and I have a divide by 12 counter, and I want to do a divide by 40. All right, so if I use the decade counter to divide by 10, and if I use the divide by 12 counter to divide by 4, then that would give me a divide by 40. Okay, so that's my plan. My plan also was that I copy and paste the circuit in there so I don't have to draw it. So now the issue is, can I do it without drawing it? This machine has multisim, right? So I can just use multisim and I'll get the 2 chips out of multisim, and then it won't be a problem.
There's 40 by 24 and 40 by 12.
Okay, so I want a 7490. Yeah.
7490 and 7492.
So a 7490 and a 7492. And I probably want them in that order. Now, clearly, I'm using an older multisim, right? And clearly, this particular generation of multisim, you'd much rather have me use it because it's more clear what you're doing. All right.
That doesn't look anything like what we have on paper, but that's all right.
Oh, bummer. So I can't use it?
Well, I'm sure you can. You can, but I'm sure I can.
All right. So I have to draw what's on the paper. Okay, I'll draw what's on the paper. No problem. You tell him. All right. So here's a here's the 7490, and clearly I'm going to ground pin 10. So I'm grounding pin 10, and pin 5. I'm hooking up to 5 volts on pin 5. Okay, so I'm doing that. I'm bringing in a clock pulse, and I'm bringing it into pin 14. Okay, then I'm going to change colors. I'm going to come out of pin 12, which is QA. And I'm going to come around into pin 1, which is the other clock pulse B. And then I'm going to take pin 8, which is QC, and I'm going to bring it out and I'm going to say that's my divide by 10 number. Alright, now the issue is, what do I do with R01, R02, R91, and R92, which are control circuits to the decade counter? Okay, so now I'm going to look in the front of my book and see if it sheds any light on that issue before I punt. Alright, so 4592, and it says that that's master reset 1, master reset 2, and that pins 2 and 3 are not connected. Oh, wrong guy. Shit. Alright, so I'm looking at 90. 90 says 2 and 3 are master reset 1 and 2, and 6 and 7 are master set 1 and 2. So, do we want to set or reset the counter? The answer is no. No, we don't. I don't want to reset it. So, for pins 2, 3, 6, and 7, I want them to all be hooked up to ground because I'm not resetting this counter or setting this counter. Okay, so now I'm going to look at the other guy, and it's a divide by 12 guy. And I'm going to take the my divide by 10, I'm going to bring it into pin 14, which is clock pulse A. And then I'm going to come out pin 12, which is QA, and I'm going to bring that into pin 1, which is clock pulse B. Okay, and I want this to be a divide by 4, so I'm going to come out of pin 11, which is QB, and now I have my divide by 40. Okay, divide by 10, divide by 4 is going to be a divide by 40. I'm going to hook up power to pin 5, pin 5, B, C, C. I'm going to hook up ground to pin 10, 10, I'm going to ground it. And then my control circuits, RO and RO. I look on the front cover of my book for the 7492. I see that that is a master reset. I don't want the master reset to be reset, so pins 6 and 7 are going to go to ground. And that's the way I would do that. Now, what I would do is I'd hook up VCC and ground first, so you get some partial credit, and then do as much of the rest of the circuit as your mind can allow you to do before you punt.
I have a question.
Yes?
You have marked up there divide by 2. Did you mean to put that up there?
Yeah, it's really divide by 12.
It says
Yeah.
divide by half on the sheet. How do you get divided by 40?
This is a decade counter. And I'm using the whole counter, so I come out of it, divide by 10.
Yeah.
This is a divide by 12 counter. So it's counting to 12 for whatever reason. So I need to get a divide by 4 out of it. So if I send it into a divide by 10 into clock A, and then QA into clock B, then QB for this guy is going to be a divide by 4. If I come out QB, I'm divide by 4. If I come out QC, C, divide by, oh, am I ever hosed? And I'm going to divide by 8. And if I come out QD, I'm going to divide by 12. But I don't want QC, I want QD. And that's what somebody was going to complain about real quick, I can tell. So QD is pin 11. QD is my divide by 10 spot. And I don't want to, I was getting a divide by 8 out of my divide by 10 counter, and that's not what I wanted.
So then what are the multiples of the decade counter? There's QA like 2 and QB is 4.
Yeah, 2, 4, 8, 10.
Okay, so there's no 2, 4, 8.
But it could be 2, 4, 5. If I went in clock B only, then QA isn't being used, and QB would be 2, and QC would be 4, and Q delta would be a divide by 5. So I can get a divide by 5 out of that guy, just like my divide by 12. So we look at the divide by 12 guy. What we get is 2 counters. We get an A counter, which is a divide by 2, and we get a B counter, which is a divide by 6. And if I hook them together, if I took the output of A and put it into B, then I'd have a divide by 12. In the divide by 10 counter, the decade counter, we have 2 counters. We have an A counter, which is a divide by 2, and then we have a B counter, that's a divide by 5. And those are, and if we put them together, we can have a 10. But if we only came in the B clock and we came out QD, we would have divide by 5.
So to get it to go up more, like if you only had the B, and if you went into like QA to QB, would that be a divide by 10 since you went in that twice?
If I came in with my clock through the A counter, and then I brought the A counter out, which is now a divide by 2, into the B guy, so that would be QA. Now I have a divide by 10, because I'm using both the divide by 2 and the divide by 5 counter to get the divide by 10.
So in 7492, when you're getting the extra 4 to multiply, gets 40, and you're running it clock pulse A to clock pulse B, you're getting 12 there?
Yes. If I come in clock pulse A and I take QA and send it into clock pulse B,
Yeah.
then
So then
I've already done a divide by 2. Now I'm going to do it'll be divide by 4 at QB, a divide by 8 at QC, a divide by 12 at QD.
Not going to clock pulse B, just using clock pulse A?
If you only use clock pulse A, the only output you're going to have is a QA, and it's only going to be a divide by 2 counter.
You
Right.
can't go, okay.
Yes. So you can't go, if you go into
So
clock
could you
pulse
use the clock
A,
pulse B then?
you can go into clock pulse B independently of A, yes. And that's why I say you can use the B counter to get a divide by 6 or divide by 5. Or you can combine them together.
So technically for this problem, you could just, you go for the 7492, go into clock pulse B and use one of the inputs that would go to 4, right? So
Yes.
it'd be A, B, and C then?
You could.
Do A, B, and C, okay.
But now if you go into clock pulse B, there's no QA output.
Okay.
Okay, so there's only a QB output
Just
if you're only going into clock pulse B.
There's only a B? There's no
Yeah.
C or D?
So there's a C and D too, but there's no A.
Okay.
The only way you get an A is if you use clock A. All right.
So then from B, is there like outputs on QB, QC, and QD, and then you kind of pick which one to put the wire to
Yes.
get the number you want?
Would be like 2, 4, and 6 in that regard.
2, 4, 6
Okay.
for the divide by 12
Oh.
guy. 2, 4, 5 for the
QB would
decade.
be 2, QC would be 4, and QD would be 6.
Yes.
Okay.
Mm-hmm.
I guess the last question is if you have a different type of counter, like divide by
200
divide by
late.
A, divide by 200, whatever, is A always first going to be divided by 2? And
Yes.
B is going to be whatever that is, half?
Yes. Mm-hmm.
Okay.
That makes a lot more sense.
But there's 2 separate counters on all the counting chips. There's an independent divide by 2, an independent divide by whatever. Yeah. Okay. Calculate the size of the current limiting resistor that could be used to limit 15 milliamps in a 5-volt system. Okay, well, we know the answer is 333, right? So we just write it down and work away. Number 3, you could do that. I mean, you know, there's no reason that you wouldn't. Okay, so is V equal IR? Does Ohm's law still apply?
So,
And if so, why? Well, because it's a law, it's not going to change. Does Ohm's law change because I'm falling into a black hole? No, it doesn't. Okay, so Ohm's law is apply. So I'm going to have my, I want to calculate R. So R is equal to voltage divided by current. Do I know the voltage? 5 volts minus the voltage drop across the diode, which is how much?
0.7.
1.4 volts for a light emitting diode. It's always 1.4 volts for a light emitting diode. Every single problem we've done all semester.
I thought it was
0.7 for a regular diode, yeah.
Okay, for regular.
Unless it's germanium, then it's 0.3. Yeah.
What numbers we have to remember?
No, but for a light emitting diode, 1.7, unless it's a high intensity one. If it's then, you don't want to hear that either. Okay, so 15 milliamps. All right, so now it's time to break out our calculator and see if we get 330.
3.6 by 15 to the negative 3.
I got the 330, rounded 330 before the subtraction of the LED.
And then I got 240. But
Oh, 240 is the right answer. Yeah, if the 330 answer goes with 10 milliamps.
that one.
So if I do it with 10 milliamps, I end up with the 330 answer.
Or if you didn't take the LED out. then-
Oh, you didn't take the LED out, right? Actually, it's 360. So 360 is the answer with 10 milliamps. But they want us to give us an answer with 15 milliamps. All right. I'm sure the key will be right. Okay. So now we got number 14. Now, obviously, number 14 is there for the 2 or 3 of the overachievers in the room. We won't mention your names, but it'll prevent the class from getting a natural 100 and embarrassing the instructor by getting an A on the test, right? So the first thing we have to decide is
So it resets.
very interesting. Okay, so does anybody have an answer for what this does? Anybody have an answer?
Light up a 7-segment display. Light up a 7-segment display in different locations.
Well, you could build it, I suppose.
What does this circuit do?
Yeah, what does it do? Okay,
Paper.
I am going to write down the answer. Okay. I'm done. That's all I have to do.
It's flip-flop, flip-flop, flip-flop.
Well, look at it. See, where is the set?
And
Is the set inverted? No, it's not inverted. Is it high? Yes, it's high. So this thing's it's setting all the time. Even if it changes to something else, it's gonna set immediately. Look at the reset. If you have 1, 1, 1 going into the NAND gate, what do you have going out? A 0. So is it resetting? No, it's not resetting. So it's 1, 1, 1 all the time. The clock happens. It doesn't matter. It's still 1, 1, 1. The clock happens. It's still 1, 1, 1.
Well, isn't it
Now,
like
clearly, the test on the exam won't be that way, right? I obviously made up the study guide. I fucked it up, and I made it so the circuit didn't work, and I didn't realize that until I printed it out. I've never changed it, right? So on the test itself, probably what's there is the same exact circuit, except our flip-flops are knotted guys, like that.
no, you don't have to.
So,
Keep it like this. Yeah.
no, but the test is already made. So if they're knotted guys, if they're knotted guys, and I've got that NAND gate there, that means that whenever I get to
Is it gonna change? Hold on a second.
whenever I get to 7, I'm gonna reset and go back to 0. So I'm never gonna see 7. It's gonna reset and go back to 0.
Well, the first flip-flop isn't it connected to the Q mount one? The node?
One's gonna go to 0, go back to 1.
I don't understand the question.
Like for the stuff that goes to the reset, if you follow the first input, it's not connected to the top Q like the other two. It's connected to the bottom one.
I still don't understand what you're trying to tell me.
So
So there's
to make it
nothing,
wouldn't
there's
reset
nothing, there's
five,
nothing wrong with the
seven.
circuit except the set and reset are not knotted, so therefore it doesn't work. So what I'm gonna do is I'm gonna work a different problem, one where the set and reset are knotted and the circuit does work in the off chance that that is the problem that's on the test because that's all that I changed. Okay, but remember that the last time I taught the class was 2010, so I don't really remember the question. It's probably something really worse than this, but we're gonna do that anyway. So back to the issue at hand, we have J, K, we have J, K, we have J, K. 1, 2, 3. That's what we have. If we start at 0, 0, 0, if that's the case, J and K are both 1 on the first guy. On the second guy, J is 0, K is 1. On the third guy, we're doing an exclusive OR of a 0 and a 1, which gives us a 1, so I've got a 1, 1 there. All right, so that's what I've got. The clock pulse happens. Boom. Okay, so the clock pulse happens. This is a toggle. This is a reset. This is a toggle. All right, so that's what happens. Now, I look back again, and now my J and my K are still both 1. My J2 is a 1. That's a 0. I look at this exclusive OR. I'm got a 1 from there, and I got a 0 from here. So these two are both 1s. All right. The clock pulse happens. Boom. I toggle to a 0. I set to a 1. I toggle to a 0. All right. I look at it again, and I say I've got a 1 and 1 both there. I've got a 0 on my Q. 1, so I've got a 0 there. I've got a 1 here. And I've got a yeah, I got a 0. I got a 0 there. And I've got a 1 there. So these guys are still in toggle mode. Okay, the clock pulse happens, boom. I've got a 1, wrong color. I get a 1, I reset to a 0, I get a 1. So, that being the case, I don't have to do anything else. I go 0, that's the most significant guy. So this is a 5, that's a 2, a 5, a 2, a 5, a 2, a 5, a 2. And that's what this guy would do if he were knotted on the set and reset. Okay? If he's not knotted, all he's going to do is go 1, 1, 1 and stay there forever. And then you'd ask yourself, if you're going to be anally retentive, which I know you will be, you will ask yourself, well, what if I start at something other than a 0? What if I start at a 1? What would happen? If I start at the 2, I know what's going to happen. But what's going to happen if I start at a 3? What's going to happen if I start at a 4? What happens if I'm going to start at a 6? What happens if I'm going to start at a 7? So this particular problem would have 1, 2, 3, 4, 5, 6 different answers if you wanted to go for all 6 of them. If you're, so let's say that you actually did watch the entire Republican debate last night, and you're that type of person that did that, then you'd want to find all 6 answers, right? And you'd want to ask those things. But this particular circuit, as drawn, 1, 1, 1. Okay. Enough of that. But that's how you'd have to do it. You'd have to go and say, the J is this, the K is that. What's going to happen on the clock pulse? For this guy, 111 would be the answer because it's constantly being set. It's always set, yes. So the Q's are always high.
I see where the J value came from for the first flip-flop, which is
Yeah.
connected to the 5 volts. On the second, I can see where the 0 for the J comes from, but where did the 1 for the K come from?
Well,
on
if
their initial
the
value.
first flip-flop is a 0, 1 for the Q and Q naught, then the K would be 0 and 1 for the second flip-flop. Because it's getting, Q is coming from the first flip-flop to the J of the second one. Q naught is coming from the first guy to the K of the second one. Yeah, so whatever the Q and Q naught are, they're being assigned to the J and J naught, to the J and K.
Okay, so the other thing with the Q naught actually. Okay.
Yeah. So if the Q is 0, Q naught is 1. Yeah. Okay.
Let's go. One on the board. What would have been the proper answer for that? The 0, 5, 2, 5, 2, 5, 2, 5, 2?
Yes. Probably 0, 5, 2, 5, 2, repeating, something like that. That would be good. Because as soon as you got another 5, you're going to go back to 2. You don't have a choice. But then you to get the other answers, you'd have to start someplace other than 0, 0, 0. So you could say, well, a cosmic ray happened, I started at 1. What's going to happen? Yeah. But I'm sure that whatever that particular question is, it's probably a 4-bit one instead of a 3-bit one, and whatever it is.
Thanks.
Yeah. Anything to help out. Bummer. Where's my sound? Control, Alt,